So this is Texas, so let's do a football example. So we've got a running back, and the running back is running down the field, and we're going to have someone else running after him at an angle like that, and they're going to tackle right up here and then move together. So they're going to, when they tackle, they're going to become one object and moving together. So we're going to call this mass 1, mass 2. So mass 1, mass of the running back, 154 kilograms, and is initially moving with a velocity of 2. Let me scratch that. The running back is a mass of 175 kilograms and is moving with a velocity of 1.85 meters per second. The defender here is moving, is going to have a mass of 154 kilograms and is moving at a velocity of 2.41 meters per second at an angle of 40 degrees relative to downfield. So the question is, after they collide and they move together, in what direction are they moving? Okay. So to do that, we're going to need to know actually the vector components of this. Okay, so the vector components of velocity 1 is just going to be 1.85 meters per second j. The vector components of velocity 2 is going to be 2.41 minus 2.41 meter per second sine 40 degrees j, because it's the opposite side of that angle right there, plus 2.41 meters per second cosine 40 degrees, that should be I, this would be j. Okay, and so V2 comes out to be equal to minus 1.55 meters per second I plus 1.85 meters per second j. Okay. Now, this is a collision problem, so it's not really the velocities we're interested in, it's momentum, because we know that initial momentum equals final momentum. Now, it's got to be the vectors. And so the initial momentum is going to be P1 plus P2, and that's going to equal the final. Okay. So P1 is going to be M1V1, and P2 is going to be M2V2. And the final is going to be M1 plus M2, because they're stuck together, times the final velocity. And so that is what we need. So we got to figure out this and this. Okay, so that's going to be my P1, and that's going to be my P2. Okay, well, that's actually pretty easy to do. So P1, we just multiply what we had there before, and that's going to be 324 kilogram meter per second J. P2, because we said that, this is 1, and then this is 2. Okay, so P2 is going to be minus 239 kilogram meter per second I plus 285 kilogram meter per second J. So the final, it's just going to be adding the two together. And so we add the two together, that's minus 239 kilogram meter per second I, and it's going to be plus 609 kilogram meter per second J. Okay, so now we got, so the final here, Pythagorean theorem would tell us that 654 kilogram meter per second at an angle of 21.4 degrees from downfield. So 21.4 degrees to the left of downfield. Okay, and so we got that by saying that 654 kilogram meter per second is square root of the x component, 239 kilogram meter per second, squared, and the y component 609 kilogram meter per second squared, and then the angle we got from the arctangent of the x over the y. So 239 kilogram meter per second divided by 609 kilogram meter per second. X over y because it's the opposite over the adjacent side. Okay, to get the angle that I wanted. And then that gave me the angle. Okay, so that now we have the final momentum. So the final velocity will be the final momentum over the total mass. So that would be 654 kilogram meter per second divided by 154 kilograms plus 175 kilograms. That comes out to be 1.99 meters per second. So the final velocity vector is 1.99 meters per second at an angle of 21.4 degrees to the left of downfield. So 21.4 degrees. So this is it right there. Okay. So always say what you're measuring relative to. So it's relative to downfield. Okay. Now, interesting thing, what's the change in kinetic energy? So the initial kinetic energy is going to be the 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Okay, so if you plug in the numbers, you get 747 joules. The final kinetic energy is going to be the 1/2, they stick together, so m1 plus m2 times the final velocity squared. That comes out to be 651 joules. So the change in kinetic energy was a minus 96 joules. Okay, so we got the final velocity, and then we got also the final change in kinetic energy. Now that would be the example of a running back running down the field and then being tackled by someone coming up from behind. So let's consider another problem. Let's consider the problem of this as a kickoff return. So now you have someone running downfield and you have the defender running this way. And so it's at an angle right there of 40 degrees. So we can say the same thing. We can say this is M1, this is M2, V1, V2. Let's say that M1 is still 175 kilograms. V1 is still 1.85 meters per second. And then M2 is still 154 kilograms. V2 is still 2.41 meters per second. So the only difference is now V2 vector is now going to be minus 1.55 kilogram meter per second I minus 1.85 kilogram meter per second J. Okay, so momentum, mass times momentum 1 is mass times velocity 1. Momentum 2 is mass 2, velocity 2. And so this comes out to be, the first one didn't change. That's still going to be equal to 324 kilogram meter per second J. Now we have minus 239 kilogram meter per second I minus 285 kilogram meter per second J. So that's the only difference is we changed that sign right there. That's the only difference that happened by making this a kickoff return instead of a defender in the backfield chasing down a running back. So total momentum, P1 plus P2, the only thing we changed was that one term. So that means that when we do this, we get total momentum is minus 239 kilogram meter per second I. That part didn't change, but the other term changed. Minus 39 kilogram meter per second J. So the total momentum is now going to be, Pythagorean theorem, 242 kilogram meter per second at an angle of, well, in this case, it's 80.7 degrees from downfield. So we're now going off this way. Okay. But velocity is going to be that magnitude of that. Okay, so there's a magnitude of it. Is going to be 242. So the magnitude of that divided by, or rather the velocity vector, even in fact, is going to be that is going to be m1 plus m2 divided into the final momentum. And so again, the masses don't change, so this comes out to be 0.736 meters per second, and the angle is 80.7 degrees from downfield. Okay. So, initial kinetic energy did not change. That was still 747 joules, but final kinetic energy is going to be 1/2 m1 plus m2 times the final velocity squared. And so now that is radically different. It's 89.1 joules. So that means the difference, which is going to be K final minus initial, so the difference here is now going to be minus 658 joules. Okay, now notice here that when we had a runner here being chased down, the change in kinetic energy was minus 96 joules. But on the kickoff return, where the only thing that you did was you changed the direction of the defender, then delta K is now going to be minus 658 joules. Okay, so that's a huge difference right there. And so where's all this energy go that was dissipated? Well, some of it goes into heat, obviously, but a lot of it goes into shaking up the brains of the players. Okay, and so this is why in football, there's debate about whether or not to do away with kickoff returns, because this is where you often get the most injuries in the game, and so that's why they're even debating that, and so this is the physics behind that.